Hello everyone and welcome to this video where we're going to look into PIDs and how to tune them. Now this is a request that many people have asked me to make, and I talked about this in my Microcontrollers 101 video. I recommend you watch that if you are beginning with your journey on microcontrollers, how to tune them, program them, make them, all that good stuff. PIDs are a sub part of making microcontrollers, and they can be very useful for engine control, regulation of throttle, depth hold, such as for submarines, and altitude hold on helicopters. Inside the workbench, you do have PIDs here as a standalone microcontroller box, or my preferred method is within the coding and programming of the microcontroller itself. Like this, you can apply two different types of PIDs. Now, of course, the difference being this one is part of the game, so the logic nodes are right there for you to use right away. It's kind of the vanilla or base game PID. I believe this is the system that Stormworks used originally before we got this style of microcontroller that we can actually code ourselves. Before we go any further with Stormworks, I have to explain what a PID is. Now, PID stands for Proportional Integral Derivative Controller, and as you can see, it's a lot of talk about coding, programming, all kinds of formulas and stuff. I'm going to try to break it down to you to make it a little easier to understand. But at its very core, what a PID controller is it uses a control loop feedback mechanism to control process variables within a system. Now that might not make a lot of sense right now, but if we click on the top one, the non-advanced or basic PID, you can see it has proportional, integral, and derivative, so PID. And it lets us put values in here. This one, it doesn't have the values built in, but what I do recommend you do if you are intending on using the advanced one, and the advanced one, the only difference is that rather than having the values here, you have them right here. So what I recommend doing if you're using advanced is you take a property number and duplicate it times 3 and apply it to all of these, and then what you can do is label them P, I, and D. And then the nice thing is when you are in Stormworks itself like this, just like this one here that allows you to change the values, right here you can change the values. So we're going to talk primarily about this one here. We're going to delete these ones, although the tuning works the same. Now, it is such a small element of Stormworks, but it has caused so much headache and problems, to me included. There's been times that I wanted to just drop the whole thing and move on with my life, but it is useful to learn because there are very, very useful applications of it. Now you can see here we have set point and process variable, and that's on both of them, set point, process variable. So what I talked about earlier with the definition of the PID is, in essence, you have a set point value that you want it to set to, and by setting it, it will adjust this one, the process variable. There's a really good simple guide to tuning PIDs by Nigel Fromage, and what you can see here is that Nigel goes through the steps to tuning a PID. In this case, he is having sort of a gimbal or stabilizer for the seat using a pivot, and the boat moves and you have the seat always staying stable. Now, this is a really good explanation. It says P, the proportional, does the bulk of the work. Imagine we're designing an auto hover for a helicopter. At first, the helicopter is too low. The difference between the target and position are very large, and the engine turns to full throttle to bring us to altitude. Once we reach the right altitude, the PID notices the difference is small, cuts the engine, the helicopter falls, and then you end up in a cycle. It goes up, down, up, down, up, down. So you can tune that, but you then also have differential. So the differential is a measure of how fast we are moving towards the target. If we are rocketing towards the target, we're likely to overshoot it. D creates an opposing force. So that is useful to us. And then this tutorial goes on to explaining how to tune it. In this case, starts with a low value, 0.1, and you see how it works. So with 0.1, if the system underreacts, moves too slowly, we need to increase P. If the system overreacts and we overshoot it, we need to decrease P. And if it moves altogether in the wrong direction, if the number is increasing when it should be decreasing, you can make the values negative. And then last but not least, here it says if the system is sort of swinging like a pendulum, then you can start with a low D value, 0.1, and if it's rapidly moving, then D's too high, needs to be reduced. It doesn't go into what the I is, the integral. There is another good tutorial by users Trapdoor and by C4V Engineering, and this one is a little bit more intense and technical, but what it does do quite well is it lists the PID as sensitivity, the I as change over time, and the D as dampening to help new players. So with these ideas, P being sensitivity, you can adjust them and end up with something that makes a little bit more sense. So this is kind of what is a nice definition. The P, or sensitivity, is how fast the PID responds. The I is the change over time, and the D is the dampening, which it adjusts when you get close to your set point. So as we discussed earlier, this section's also nice. Kind of shows you the numbers and values that the PIDs usually end up. So the user here says that the numbers usually end up being 0.5 for P, 0.00001 for I, and 0.1 for D. But the starting point would be to use just 0.1 for P, 0.1 for D, and 0 for I for now. Now there are sometimes wild things, such as this, that don't make any sense. If you have P set to 0, that's the main number, and then you have a high I, like 5, D is 10, that doesn't really make sense, and that is kind of confusing. So what you'll want to do is have your numbers something along these lines. Now I have had instances where my P ends up being 2 or 3, but the I is always 0 or super low, and the D is usually less than 1, maybe 0.5 at its max. So to test this out, I have this helicopter. I've made it in a previous tutorial, and down here we have the altitude hold. Now a very simple microcontroller here. In essence, it just pulses your current altitude, and it uses that as the set point. So the one that is saved when you've pressed the button, that is the set point. If you pressed the altitude at 20, you want to stay at 20. And if your helicopter starts to go down, your current altitude is maybe 18, it's got to kick in and hit that 20 again. So if we set everything to 0 and you turn on your PID, nothing will happen. It's as if there is no PID. So having everything at 0 doesn't make any sense. What I recommend doing is setting the proportional to 0.1 and seeing what happens. With our helicopter, if I press the hold button, you can see it sort of looks like it's working. And if we look at the numbers, it seems to have done the trick. So in this case, it's keeping the altitude pretty much where we need it to be, where we wanted it to be, and it's micro adjusting. It was going down, now it's going up a little bit. How far it will go up, I really don't know. I don't want to keep sitting on it, but that is probably okay. Now keep in mind, it did that because we were already at the altitude we want it to be when you press the button. What happens if we are ascending, such as this, and press the button? Boom. Now it's going to go up, it's going to go down, and then it's going to go up and self-correct. So you saw how I hit it, but at the moment I hit it, it was at 57. It went up to 60, and then it went down and back up. So even with that test, it seemed to perform pretty good. I can do it also when I'm going down. I'm going down, I'm going to hit this button, and it kind of overshoots, corrects, and makes its way back up. I would probably put a value regardless as my derivative, even if it's just 0.01, just to have, personally. What that should do is give us a bit nicer kind of smoothing, if you will. So it will sort of oscillate a little bit, but it will end up in a value that makes sense to us. So again, if we're going down and we hit this, it corrects itself and it stays at that altitude. Now, by having different weighted helicopters and things, you may have to adjust this number. It may not be the end-all be-all for everything. This is a quite small helicopter, but you can see it's doing it absolutely perfectly in this case. Another neat thing with PIDs is it allows us to use a velocity pivot as a robotic pivot. And the nice thing about that is the velocity pivots have a motor power of 1000, where the robotic have 200. So this one is 5 times more powerful with the motor. But when you attach the node from your throttle lever to the rotational velocity, as you saw, it just turns on a speed and the thing can spin on forever. So this is where you can use a PID. So in this case, we even could use this one here. And what we'll want to do is have the current rotation be the process variable. And the lever, throttle, will become the set point. So we set something on the lever, it will adjust the process variable until it matches what we have on the lever, and it will do it by adjusting the control output, which is the rotational speed. Now in this case, active, it can always be active if we want, so we can just put a constant on, doesn't really matter. But what we need to do now is tune this thing. So let's try off with that 0.1, 0, and 0 right now. At what? The pivot measured rotation expressed in fractions of full turns. So what we can do is, first of all, let's set this to 0.25 and 0.25, and we can change this now. So we're going 0.25, so we want the current rotation to be 0.25. You can see it's taking way too long, regardless. So we got to up the speed. And we can do that by changing the proportional. So let's put the proportional to 1 in this case. With it at 1, we set it to 0.25, and there it is hitting 0.25. And you can see it's kind of making its way slowing down, and boom, it's hit 0.25. If we go in the other direction, we can see that it's kind of making its way slowly, and it will be there in a few seconds here. Boom, there we are. So that was good, but it wasn't perfect. You can see that it slows down drastically as it comes to that final point. That said, we don't want it to overshoot the mark, but we don't want it to kind of be stuck. So we can just ballpark a number. Let's put 2 proportional and 0.5 derivative. So with this setup, you can see it makes its way there much faster and stops. Now, likewise, we go there, and there we are. So we can watch how the behavior of this arm works. So I would say that this system works. I mean, it does kind of slow down as it gets to the mark, the final mark there. So you can play around with the values until you end up with something that you're happy with. You kind of want it to make its way there. Now, whether it's at 0.25 or in the decimal points, it really doesn't matter at that final stage. But it does seem to kind of work okay. It does take a little bit of time to get there. So in this instant, I'd probably lower the sensitivity of my throttle itself to allow the PID to catch up to it. You can see here, now it still takes a little bit of time, it has a little bit of delay. So what if we set this to like 5 and this to 1? In this case, you can see here, the second we let go, it stops moving. It pretty much acts like the robotic pivot with this in mind. So it seems to work quite nicely. This is a perfect example to show you what happens if we set too high of an integral gain. So if we put 0.1, you're going to see here now, as I move this, it will swing back and forth. You see how it kind of overshot the mark and makes its way back. And then you kind of end up with a bit of a pendulum type situation for a little bit. So you do have to be a little careful there before setting too high of a value for your integral. Now we saw that 5 works quite well. If we set it to 1.1 and 1, what will happen? If we set this there, and you could see it now, it really exaggerates the pendulum. So if you end up in an instance where you're getting this type of pendulum action, you have to go back into your PID controller. First of all, lower your integral and also lower your derivative. So with those two things done now, you shouldn't have that pendulum effect. Now the pendulum effect, you may want that in some instances because you might not want it to slowly hit that level, especially if it's something that you're constantly moving. For example, the altitude hold, if you want it to set at like a level balance, you want it to have a little bit of springy motion. Another useful thing with PIDs is as a RPS set or hold, but there's a lot of parameters and factors that go into that, including the loading on the engine, the gearing, the strength of the engine. This one's also supercharged with, which may also cause a detrimental effect in terms of the power and capability of the engine, because when they're supercharged, they actually have air, and then the air has a limit. So what will happen is the air will flood the pipe here and cause it to not work so well. So what I do have here is an RPS hold that I'm trying to set to 14, and I'm tuning the PID, sort of going through the steps, but even still I've been spending around 10 minutes jumping back and forth, adjusting these parameters, and ending up with something like this. So my advice is, even if you think you can tune a PID fast, you might be able to, but you can end up with the odd instance where it ends up sort of draining you. And if that's the case, take a step back and see it at a later date. So I suggest playing with the P and the D primarily until you end up with something. The I you don't really need to play with too much. You can see here it's hitting that 14, but it's jumping around way too much. And now is when I would plug in a very, very small I and see how that affects the system. So like I said, even for me, it's not a walk in the park. There is no one-size-fits-all solution. You can see here, this is possibly worse. So you do have to just kind of go at it until you end up with something that seems to work. If you lower it too much, such as what I just did now, it won't even hit your target RPS or whatever you're trying. So you see here, it's not climbing fast enough. But something a little higher would help it, albeit something a little higher would also make it such that it overshoots, overcorrects, all that stuff. So you see here, as long as the numbers aren't jumping back and forth too fast, it's okay, but we're quite slow to reach that 14 RPS that I want. So tuning is important. Patience is more important. And there are certain things that you can do to help you with that tuning process and procedure. But like for this, even if it hits 14 perfectly, this is a fail. It's not going fast enough. So we'd have to turn up this. So you see, it is a bit of back and forth, trials, testing, and even for me it is. So that's kind of just the takeaway that I recommend you all to approach this with, because even if you end up learning the basics, the actual principle of the coding and tuning it do take a little bit of time, depending on your specific system and your specific needs. So that is sort of what I hoped to show in this video. Hopefully everyone learned something. Hopefully the little bits of information are useful to you. And the rest, I wish you luck in tuning it, in making your PIDs work. If you are interested in learning more, there are a ton of resources on the internet that you can apply your knowledge to and read and find out about how things work and why they work a certain way. In this video, again, the purpose was to more so make it an easier approach to understanding. See, now we've overshot it. And a little pro tip for those of you who are still here: instead of jumping back and forth into the microcontroller as I've been doing, what you can also do, and will make it infinitely easier for programming, tuning, testing your PIDs, is use the advanced controller like this, and not this one. And rather than putting in what I just told you, which is the property slider, what if you made it into a node? So you can actually make nodes that are for each one of these, the P, the I, and the D. And this will allow you to, in real time, in the game, change them on a keypad and make them so that you can see the adjusting factor on your creation right there and then. By connecting the P, the I, the D into these right there, and here in the game itself, setting them on a simple small keypad, you can test out all this that we are doing without jumping back and forth. So if what I would even recommend is making a test platform that allows you to test out your microcontrollers or your PID controllers without having to go back and forth. So there you have it, a little bit of a pro tip. This allows us to set the P and the D right away to 0.1 and see what happens with our RPS. And then we can adjust it as needed until we end up with a result satisfactory to us. See what happened there? It kind of jumped. So now we could turn this up. We could turn this up even more. Make this even 1. Now we're back to there. We can adjust this. So anyway, it lets you play with it in real time without having to go into the game itself or into the workbench itself. So with this, I think this is an extremely useful resource and just a big time saver. Even if you have no idea what you're doing, you can change values to your heart's desire until something resonates here. Anything's possible. Didn't quite hit 14, but just under 14 at 13.3 using 0.3, 0.00001, and 0.0001. Now we can adjust these. Let's see if 0.0002 changes it drastically. Or what about 0.002? What about 0.005? So it really does let you play with the numbers, assuming you just have the patience. And in the end, we may get to something that actually lets us hit the number we want. Oh, look at that. So, it was quite happy being a low D. And then if we turn this up, it should let us come closer to that point 14, or that 14 throttle mark, hopefully without causing too much instability. So you see here, as I turn this up, oh, now it's back to revving. So patience is the key here, and just slowly testing the numbers until you end up with a system that kind of balances itself and is stable. Thank you all for watching. A huge shout out to all of my supporters. They're listed here on the left. Thank you everyone for watching, for participating, for being a part of these videos, and stay tuned for more content and creation. Until then, happy Stormworksing everyone.